how to get the potential of a continuous charge distribution, just like we did for electric fields. So far, we've been concentrating on point charges or systems of point charges. So now let's assume we have a continuous charge distribution, like a rod, or we could consider semicircle again, or we can consider a ring again, or we can consider a disk. And we can ask the question, what's the potential at any point along the x-axis? What's the potential at the center of this? And what's the potential for the rod? Actually, we can ask the potential at any point. We don't need to use symmetry, okay? Because the rod is, since potential is a scalar, we don't have to worry, oh, okay, the electric field is this way, electric field is this way. It cancels the x components, okay? The potential is a scalar. So this is the cases that I'll do. So let's look at a uniform charge rod. You know what I can do? I can develop a general equation that I can apply to all points. Let's assume, let's put the x and y axis at the end of the rod. Okay. Find the potential at the point xy. Or let's say, yeah, that's fine, xy. Okay, so you take a little piece, and each piece creates a potential there, right? And then we integrate over the length of the rod. So we say the distance here is going to be, you know what, let me give this thing AB, because you'll get confused with, well, let's call this AB. And then this is the point of the rod x. So this distance is going to be a minus x. This thing is going to be b. Right? So my potential dV is going to be k dq over this distance. K dq over the distance a minus x squared plus b squared, right? And then to integrate the, and then remember we say dq is lambda dx. So those similar techniques that we had when we were doing electric field comes in here, but the only difference is potential is a little simpler. Actually, it's, I would say it's quite simpler. We don't need to worry about directions, you see. So, K dq is lambda dx. So that's how you would do it. And then the lambda would come out of the integral. You would go 0 to L. And if this had actual numbers, you could either put it into the TI 84, 85, you know, put it into the TI and do the definite integral. Or if you could have TI 89, you could just do an indefinite integral and then put the numbers later on, you know. Let's see, what is this integral? Is it one of the easy forms? Anyone recognize that? Let me bring the calculus book here. That's probably Okay, so what is that form there? 1 over square root, let's look here. It's going to be ln, right? And then it's going to be u, so it's going to be x. Oh, okay, you know what's going to happen? I say let u equal a minus x squared, a minus x. So du is going to be negative dx. So I can integrate in terms of u and then change the limits of the integral, right? So let u equal a minus x, du equals negative dx. So I'm going to have k lambda ln of x plus, and then it's going to be u squared plus x squared. Or let me just put here, let's see. Let's put u squared. You know what, hold on. My u is this one. So that's going to be a minus x plus square root of a minus x quantity squared plus b squared. Absolute value. And the limits of the integral. Well, actually, I could keep the limits of the integral, right? If I plug back the u. So if I plug back what u is, a minus x plus square root of a minus x squared plus u squared. And then over here, I'll just change the limits of the integral. I'll just swap them, L to 0, right? Negative du. Okay, so if I put 0 here, what am I going to get? Natural log of 0, it's going to be a plus square root of a squared plus b squared minus ln of, and you put L, so you have a minus L plus square root of a minus L squared plus b squared. That's as general as we can get, right? And then you could put in what the lambda is, q over L. Okay? Now, if you want, you could do the two limiting cases here. You could do the limiting case where the A is in the middle or A is here. Remember, for the electric field, we found the potential in the middle axis and at the end. So we could put here A is equal to L over 2 and B is equal to whatever. And then you could put here the distance 0b into our general formula. So what we did is we derived the most general formula for the potential of a rod. And then we can now say V in the middle, in middle axis, is going to be what? So now you can put A is equal to L over 2 over here. Ln L over 2 plus square root of L squared over 4 plus B squared